Molecular geometry. Molecules are three-dimensional objects. Their shapes affect their properties. In order to determine the shape of a molecule, we use valence shell electron pair repulsion theory, otherwise known as VSEPR. According to VSEPR theory, the molecules will adopt a shape or geometry that will reduce the repulsion between the bonded electrons. The electrons want to be as far apart as possible because they are all negatively charged, and the negative electrons repel against each other. If you want to see more about this, click on the red box to view a simulation. VSEPR numbers. Teaching and understanding molecular shapes can be difficult. A system has been developed using what are called VSEPR numbers, which will greatly simplify your understanding and your ability to teach this subject. VSEPR theory assigns a 3-digit code to each molecular shape. To determine this code, we must first sketch the Lewis structure. Step number 1, the first digit of the VSEPR number is the total number of electron domains around the central atom. That means the total number of bonds and lone pairs. Double and triple bonds count only as one electron domain. Now remember, this is for the central atom only. So in the first case, we look at boron. Boron has 3 single bonds, so its VSEPR number, or at least the first VSEPR number, is 3. In the case of xenon tetrafluoride, there are 4 bonds, 1, 2, 3, 4, plus 2 unbonded pairs, 5 and 6, which makes the first number of the VSEPR number for this compound 6. Now let's look at ozone. So 3 electron domains would be 1. Remember, double bonds only count as one domain, so this would be 2, and this is 3. Electron-Domain Geometry. The first number gives you the electron-domain geometry, otherwise known as EDG, the shape of the molecule including all bonds and 2 lone pairs. 2 atoms, or an atom and a lone pair around a central one, will form a linear shape with bond angles of 180 degrees. 3 atoms, or lone pairs around a central one, will form a trigonal planar shape with bond angles of 120. 4 atoms, or lone pairs around one central atom, will form a tetrahedral shape with bond angles of 109.5 degrees. 5 atoms, or lone pairs around a central atom, will form a trigonal bipyramidal shape with bond angles of 120 and 90 degrees. And finally, 6 atoms and or lone pairs around a central one will form an octahedral shape with bond angles of 90 degrees. Now, let's take a look at how we do the bond angles. And this is very difficult to do on a 2-dimensional shape looking at it. So what I suggest to you to do is get some model kits and pull out model kits and make these. They are set up to make models with all of the different EDGs, and it's very useful for you to look at it. Let's look at trigonal bipyramidal here to begin with. The bond angles. This bond angle right here between here to here is 180 degrees. This angle here is 90, and these angles across here are 120. Like I say, it's very hard to visualize, and it is very useful if you get some model kits to help out. And here's a quick summary of what we presented on the last 2 slides. This is a summary of molecular shape and VSEPR theory electron-domain geometries. So if you notice, I'll have the basic generic formulas in the first column on the left. So, first column, you have the formulas. Then right here, the number of unbonded pairs on the central atom. And there are the shapes, the bond angles, and an example compound. Will you need to know these for the AP test? Absolutely you will. So you'll have to have your students memorize the bond angles that are associated with each shape, and understand that as you add unbonded pairs to the central atom, it will change the shape because those unbonded pairs have a greater influence and a greater repulsive force than do electrons that are in bonds, because electrons in bonds are shared and therefore will not have the same effect as an unbonded pair.